3 months! We know it, we've looked at everything, this is the exact time it will take to complete our next project. I am so excited. And just last time you had a 3 months project, how long did it really take? 6 months, but it was completely different. We had a couple of things we didn't anticipate, we had problem with the infrastructure. Now this time it's different. Yeah, different, sure, yeah, absolutely. But what could go wrong? So, no. Okay, I think it's time for us to look at the things less obvious about time estimate and forecasting. When will we be done? This is often the very first question we ask ourselves when we start a new piece of work, especially if it's not a simple task that we know will be completed in a few hours. And it is a very valid question, simply because in any system where money and time is not limited, making strategic decisions based on effort is just vital. Yeah, well, we know how it works. We give an estimation for so-called strategic decision, and then we end up committed with way too much to do and unrealistic timelines. Yeah, it is a comment that I've heard way too often. People are scared that any evaluation of effort will translate into an automatic commitment. To be fair, very often by teams who already have way too much on their plate. But again, how can we push less work into the system if we have no idea how much said system can produce? So, second time you use the term system with no explanation whatsoever. Oh, yeah, fair call. Okay, context. I will often use the generic term system or system of work to describe any kind of organizational structure that produce value through interconnected groups of people. So a team is a system, a team of teams is a system, a tribe, a business unit, whatever kind of structure or group of people you have, that is a system. Okay, so now that's because of us and because we don't estimate efforts that we end up with way too much to do? Well, no, maybe not the only factor, but it doesn't help, and you're potentially shooting yourself in the foot by not evaluating your own capacity. And if you don't, I guarantee you that someone else will do it for you. But okay, there is so much unknowns. We are bound to end up with something completely wrong, so what's the point? A very valid argument. You're absolutely right. More than valid. This is based on a project management concept called the cone of uncertainty. It is the idea that at the beginning of a piece of work, the uncertainty is at its highest, but that as the project goes on, this uncertainty might decrease. It is actually not a guarantee. You need to actively work to reduce that uncertainty. This concept was formalized into models that have been validated by work from NASA. And research from Boehm in 1981 has even evaluated that in software projects, the uncertainty at the beginning of the work was in general of a factor of 4. Which is massive. Can you imagine? At the beginning of a project there is so much uncertainty, then work can take up to 4 times longer than originally planned. Now, I don't know for you, but it seems that even with that knowledge, with all this data and research available, we still keep underestimating everything. As Douglas of Stater described, it always takes longer than you expect, even when you take into account of Stater's law. Even when we know that things always take longer, it still takes longer. What could be so potent to fool us even when we are fully aware that we are being fooled? Oh, let me guess, a not so obvious cognitive bias? Correct? So predictable. We already talked about cognitive biases in the first video on this channel, so if you haven't seen it, please go watch it. Link in the description. And the one that interests us today is called the Planning Fallacy, discovered one more time by Amos Tversky and Daniel Kahneman. The same Daniel Kahneman who wrote this book on cognitive biases, where you will also find a pretty good explanation of the planning fallacy. So you read one book and now you're gonna reference it in every video? So careful, the planning fallacy was mentioned much earlier in a paper from Kahneman and Tversky in 1979. In this paper, they tell us, I quote, "The prevalent tendency to underweigh or ignore distributional information is perhaps the major error of intuitive prediction." Well said. What? We understand nothing. So the major error of intuitive prediction, roughly, that's our initial problem, our tendency to underestimate. Now, what is that distributional information they talk about? For that, we're going to need an example. So let me tell you a story. Let's say you and your team are about to embark on a new initiative. You're very familiar with that kind of work and you're very excited. There are some unknowns, but you are confident. You have a strong relationship with the other team you need to collaborate with, and you are all experts in the technology. So after a long workshop, talking to product managers and other stakeholders, after a long discussion between yourselves where you broke down the work, analyzed the risks and the unknowns, you have a pretty solid plan. And you think you will be done in about 3 months. You mean the same 3 months you had in your intro? Now, sudden doubt, or actually potential genius insight, you ask your group the first following question. When you were working on similar work in the past, how long did it usually take? So here we have 6 months, here 12 months, here 10 months, another 9 months. Okay, so you start to see that something is a bit off, so you follow up with this question. How much better is our team and our plan compared to the one you had when you embarked on similar journeys? Silence in the room, followed by a unanimous, about the same, maybe slightly better. Given that new information, what do you think is a much more realistic forecast for our work in our story? I mean, at least 6 months, probably even more. Yes, most likely. But unfortunately, very often we do not ask ourselves those questions, and even when we do, we tend to ignore them. That data from past projects, initiatives, or stories is the distributional information that Kahneman and Tversky talk about. Or, in their own words, we suggest that more reasonable estimates are likely to be obtained by asking the external question, how long do such projects usually last? And not merely the internal question, what are the specific factors and difficulties that operate in the particular problem? And it is that external question that Kahneman now calls the outside view that needs to be central to any kind of time estimation exercise. So, if I go back to our example, the fact that we know the technology well, that we have a good relationship with the team we need to collaborate with, all of that are the specifics of that particular initiative. This is the inner view. This is what System 1 focuses on. How long it usually takes to complete such initiative, statistical historical data on that, is the outside view. We therefore need to build a discipline to rely on this outside view rather than on the inner one. And to apply that to the context of forecasting or time estimates, Bent Flyberg, a Danish economic geographer, formalized Kahneman and Tversky outside view into a method called reference class forecasting. As always, you'll find the research paper in the description. So this reference class forecasting, what does it say? Flyberg often refers to project, but I will generalize here and use the term unit of work. So that could mean tasks, initiatives, projects, story, whichever way you decompose and organize work in your organization, this is going to be a unit of work. So here is the therefore generic reference class forecasting definition. So the first step is the identification of a relevant reference class of past similar unit of work. We are looking at our work and we're trying to find a reference class which is similar to it. The second step will be establishing a probability distribution for the selected reference class. That is our outside view. We talked about that. That is the historical data from past similar unit of work. And then the third step is comparing the specific unit of work with the reference class distribution. So what this means, particularly step 2, is that we will need to build that historical statistical data, because without it, we can't do much. And you actually might have that data if you're already one way or another measuring the time it takes to complete a unit of work, especially large ones. Okay, so you want us to fill up timesheets now? No? Absolutely not. If you're already tracking time to be able to invoice different customers or because of other financial reporting reason, then you already have that data. So my point is, just don't discount it. Recently, I was asked my view on how costly a new integration would be. Instead of guessing or asking my team to sit into a lengthy workshop, remember, that is the inside view, I simply went and looked at the historical data I had available on past similar integrations that were done by the same team. That is the outside view. And I came up with what is probably a very valid and accurate forecast in less than 5 minutes. If you have that type of data available, it is a perfect, valid outside view that you should absolutely use. Now, I fully recognize that that type of time tracking of financial data has its limit. For finer month-to-month or iteration-to-iteration type of forecasting, it will just not fit. Okay, in this case, isn't it where you would use something like story points? That is one option, but not the only one. Story points is a concept popularized by Mike Cohn. Here, the term story referred to the unit of work that he was advocating for, namely user stories. But we will again apply that to our generic unit of work term here. The basic concept is to apply a coefficient or points to each unit of work. And obviously 2 points means twice as long as 1 point, right? Not exactly, but ultimately it is completely okay if you think like that. But let's go back to our reference class forecasting. The points are actually a method for us to establish all our reference classes. So, the 1 pointer unit of work, they are all part of one class, the 2 pointers another class, 3 pointers again another class, etc. And the only thing we're gonna add on top of that is to say that anything which is 2 points is bigger or more complex than something which is 1 point. And that bigger, more complex criteria, as well as comparing every unit of work against each other, will be a very fast and easy way to put points on every of those units of work, effectively establishing a reference class for each of them. Let me show you. You can just draw a line on a whiteboard saying left is small or not complex, right is big or complex. Now, all you have to do is to place all of those units of work against this. You will quickly see clusters appearing. So the first cluster will be our 1 point, the second one our 2 points, then the 3 points. After that, we tend to jump to 5 and then 8 points. This last bit is just a technique to take into account the growing uncertainty as a unit grows in size and complexity. But again, let's simplify. To the core, the only thing we're doing is assigning a category to each of our units of work based on their relative size and complexity. And for those of you who are dealing with substantial backlog with many pieces of work, this is a very efficient technique where you can point everything in record time. It in general took me only an hour to point up to 50 items with the teams I coached. Okay, and then I guess you have historical data for each points category, so you apply the average time it takes to complete a 1 pointer, same for a 2 pointer, and so on. In theory, you absolutely could, and that would be a perfectly valid type of reference class forecasting. However, the story points technique is doing something else and is adding a second layer with an additional reference class, the velocity. What? This is so convoluted! Actually, it's quite elegant, but I must say I've seen so many teams being confused by that concept that I do tend to agree with you. This additional reference class is actually a time box, in general 2 to 4 weeks. And what we're going to assume is that for each new iteration of that time box, the same amount of work or points can be achieved. Our historical data on this new reference class is then simply the average total points we managed to deliver during that time box. So if in average you deliver 15 points worth of work every 2 weeks, then your velocity is 15. And so when you combine these two information, the points on each piece of work and your velocity, you're now able to use this outside view to forecast when you expect each piece of work to be completed. Okay, what about something simpler and even more elegant? Yeah, that would be nice. Okay, only one reference class, but I guarantee you this is so elegant your brain will fight it. Well, at this point, nothing to lose. So let's consider that we only have one reference class. So all our pieces of work will have to fit into that unique class. And if we find some that do not fit, Well, we'll have to break them down into smaller pieces until they all fit into that reference class. We can also add a couple of checks to better define that unique class and make sure we detect when a piece do not fit. It can be as simple as can be done in 3 days or less. So we flip it. Instead of making sure we find the reference class, we just make sure all our work fit into the same category. Basically, yes. And then we simply have to count all the work we're able to do in a given time box, effectively measuring our throughput. So you mean instead of pointing work, we simply count it? And that is grounded in science? Are you trying to fool us here or what? Look, at its core, it's just a highly disciplined application of reference class forecasting, and it does rely on the outside view that Fluberg formalized. Now, when we are talking about throughput, we're entering the realm of lean flow theory and queuing mechanics, which has a massive, mathematically heavy body of research behind it. And I'll be completely honest, we do not have the time to unpack the complex calculus that sits behind it, nor do I think that you would want to. Yeah, no. So if you want us to do a deep dive into heavy mathematics, well, let me know in the comments, but as for us today, we're simply gonna have to rely on the anecdotal evidence. And if you want to search about story counting or task counting or even the hashtag #NoEstimates, you will find plenty of experience reports. Okay, but let's be serious here. Is it really realistic your thing of breaking down all the work into one unique reference class? I mean, you talked about the cone of uncertainty, so you know that at the beginning of a big unit of work, it's really hard to break it down fully. You're right, but there is actually several ways to handle that. For me, I will always remember a team I worked with. Each time a piece of work was either big or had many unknowns, they simply flagged it. Later on, when the time came to work on it, they then broke it down so that it all fit into their unique reference class. My only contribution was to look into their historical data and find the average number of reference class unit of work they ended up with after breaking down those rather large or unknown pieces. With that new distributional information, we were able to forecast almost anything that came their way. And the accuracy of that forecast surprised them as much as it did surprise me. Now, it can't be that simple. And that is the thing with forecasting. It is so deceptively simple, the only thing you need is discipline. The real problem is that it can be quite complex if you truly want to understand why it works. And that lack of understanding, coupled with a fear of uncertainty, result in this belief that many pieces of work cannot be forecasted, and stops many teams and organizations to adopt those techniques. Forecasting is a simple yet complex tool, but I truly believe that any team and organization has to learn how to use it. Now, a word of caution. At scale, on really large projects or programs, forecasting alone is actually not going to help you. What? What was the point of listening to all of that then? At scale, when many teams are involved, forecasting, especially if done in isolation, will not be enough. The vast majority of large programs blow their forecast because of not properly managing dependencies and bottlenecks. You're going back to flow theory. I know. So if you like that video, well, first, let me know in the comments. Like it, share it, to make sure you do not miss the next video, potentially about flow theory. Consider subscribing, and please tell everyone around you about the things less obvious you heard today.